Hello physics students, welcome to our video on kinetic energy. We have a lot of kinetic energy going past us on the screen watching that cheetah. We are going to talk in this video about how work and energy are related. We're also going to talk about kinetic energy and the work kinetic energy theorem. So what is the relationship between work and kinetic energy? We're going to look at this from a mathematical perspective for a moment, so just bear with me. We know that net work equals force times the displacement. We can substitute, we know force equals mass times acceleration, so for the force we can substitute mass times acceleration into this equation. And we get net work equals mass times acceleration times the change in displacement. We also know from our kinematic equations that this is true. Final velocity squared equals initial velocity squared plus 2 times acceleration times the change in displacement. If we rearrange this equation in terms of acceleration, it would look like this. You can go ahead and pause the video and do the math, but that's just algebraically rearranging this equation so that it looks like this. We can substitute this, since this equals the acceleration, we can substitute all of this into our value for acceleration right there. When I rewrite that, the equation looks like this. My net work is going to be equal to the mass times the acceleration, which is all this, replacing the value for acceleration, the variable for it, times delta x, my change in displacement. Now my change in displacement, those cancel out, and when I distribute the mass to the different terms here in my equation, I can rewrite this as follows. I get my net work equals 1/2 mv squared for my final velocity minus 1/2 mv initial squared. Now this should look really familiar to you, at least part of this. 1/2 mv squared. You all recognize this as kinetic energy. In physics, 1/2 mv squared represents the kinetic energy of an object with a mass of m and the speed of v when we treat that object as being a particle with a point mass. And that's kind of how we assume things in physics so that we're able to carry out these calculations. So this is the formula for kinetic energy. And we will talk about the work kinetic energy theorem in a moment after we make a few more comments about kinetic energy. So here it is rewritten. Kinetic energy equals 1/2 mv squared. It is the 1/2 times the mass of the object times its speed squared. Kinetic energy is a scalar quantity, and the units for kinetic energy are the joule. Recall that joules are also used as the basic unit for work. Realize that kinetic energy depends on both the object's mass and its speed. So if an object at a particular velocity has more mass, it's going to have more kinetic energy than another object at the same velocity with less mass. Also, two objects that have the same mass and different speeds, the one with a higher speed will have more kinetic energy. So kinetic energy is very dependent on both of these factors. Let's look at an example. Let's say we have a 7-kilogram bowling ball moving at 3.00 meters per second. How much kinetic energy does the bowling ball have? Next question, which I should have capitalized that, sorry about that. How fast must a 2.45 gram tennis ball move in order to have the same kinetic energy as the bowling ball? And is that a reasonable speed for a table tennis ball? So start by looking at our bowling ball. We know that for the bowling ball, the mass is 7.00 kilograms, the velocity is 3.00 meters per second. We can choose our equation. Kinetic energy equals 1/2 mv squared. We can plug our values in. 1/2 times 7.00 kilograms times 3.00 meters per second squared. That will give us an answer of 31.5 joules. Remember that when we square this value, the units are also squared, so it ends up being 9.00 meters squared per second squared. And a kilogram meter squared per second squared is a joule. So we get 31.5 joules for the kinetic energy of the bowling ball. Now let's look at the second question. How fast must the tennis ball move in order to have the same kinetic energy as the bowling ball? So I'm just going to call it a tennis ball. It's a table tennis ball. But for short, I know, what do I know? I know the mass of that table tennis ball is 2.45 grams, and the kinetic energy is going to be 31.5. I want the same kinetic energy. Then I want to find out how fast it must be moving. So I'm going to use the same formula. Kinetic energy equals 1/2 mv squared. I'm going to plug my values in for the mass, for the kinetic energy, and then I'll calculate what is V going to need to be. Remember, it's V squared. So I will need to do all the math and then take the square root. Once I get the velocity squared on one side of the equation, I can take the square root of both sides, and I get V equals 159 meters per second. Now my last question in this problem, is this speed reasonable for a table tennis ball? Well, I know we don't usually think of objects traveling in meters per second, but when I do the math and convert this into miles per hour, that would be something a little more tangible for us. And when I do that, I get an equivalent of about 356 miles per hour. That's entirely too fast for a tennis ball. Therefore, for this table tennis ball to approach the same amount of kinetic energy as this bowling ball, it really wouldn't reasonably be able to do that because this is really fast. So back to our question, how are work and kinetic energy related? We're going to now talk about this work kinetic energy theorem. The net work is equal to the change in kinetic energy. This is a really important idea, and it's kind of an interesting one because we know that the units for work and kinetic energy are the same. And this theorem, this relationship between work and kinetic energy, is really important in being able to think about how things really work. In order to use this theorem, we first must take into account all the forces that do work on the object. So net work must include all of the forces doing work in its calculation. From the theorem, though, we can see that the speed of the object increases if the net work done on it is positive. Because remember, kinetic energy is 1/2 mv squared. It has to do with the speed of the object. So if the speed of the object is increasing, the net work done on it will be positive. If the object's speed is decreasing, the net work done will be negative. This theorem also allows us to think of kinetic energy as the work that an object does as it comes to rest. It can also allow us to think about the amount of energy stored in the object. For example, if we think about a hammer hammering a nail, striking a nail, the hammer has kinetic energy, and therefore it can do work on the nail since it has that kinetic energy. So let's look at an example where we use this theorem. So our example we have is that on a frozen pond, a person kicks a 10.0 kilogram sled, giving it an initial speed of 2.2 meters per second. How far does the sled move if the coefficient of friction between the sled and the ice is 0.10? First, let's write down everything we know. So these are some of the things we know. We know the mass, the coefficient of kinetic friction. We know our initial velocity. The sled has been set in motion with an initial velocity of 2.2 meters per second. We don't know what the final velocity is or the distance that it's going to travel. This indeed is what we want to find. We can also write down in a diagram form the direction our displacement is going and the force of kinetic friction is, and that will help us understand the problem better. So my initial velocity is going in this direction, and my displacement is in this direction, and my force of kinetic friction is in the opposite direction of the displacement. So I'm going to approach this problem using the work kinetic energy theorem and write that down as my overarching relationship. It's going to take a little bit of work to fill in all the blanks from there. I also know that my net work is equal to net force times displacement times cosine theta. So I'm going to write that down. I also know that the net work done on the sled is provided by the force of kinetic friction. So I am going to write that down. I know that the force of kinetic friction is equal to the coefficient of friction times the normal force. I also know that the normal force equals mg, so I'm going to write that down. Now I'm going to substitute this in to my net force because that is what is contributing, to my net force, my force of kinetic friction. Now let's look at the right-hand side of the equation and see how we can think about this. Right now, this is a known value. The mass is known. I know what this value is. I know my theta, and I do not know my distance. That is what I'm wanting to find out. So right now, I only have one variable that I am wanting to solve for ultimately. So let's look at the right-hand side of the equation and see if we can figure out how we can get a value for the change in kinetic energy. I'm going to write down that the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. And the reason I want to do that is that I know my final kinetic energy is going to be 0 because the sled does come to a complete stop. So because of that, this value will be 0 minus the kinetic energy initial. And my initial kinetic energy is simply 1/2 mv initial squared, because that's the initial velocity. It's my initial kinetic energy. So I can substitute this in for the initial kinetic energy. Now I can simply start plugging values into my equation and chug away on my calculator. One thing I didn't write over here, though I apologize, is that theta is equal to 180 degrees because the displacement and the force of kinetic friction are in opposite directions. That's 180 degrees. So as I plug these values in, mu sub k is 0.10, m for mass is 10.0 kilograms, g is 9.81 meters per second squared, d is the variable I'm solving for, cosine of theta, theta is 180 degrees. Now I'm going to say equals, 0 is simply 0, so I'm not going to include that term. I have a negative 1/2 times my mass again is 10.0 kilograms, and my initial velocity is 2.2 meters per second, and that is going to be squared. At this point, I can simply plug away on my calculator and do the algebra, and when I do, I end up with a distance of 2.5 meters. So for an advanced idea, try using multiple approaches to solve some of those practice 5C problems. See if you can get the same results. You should, but just see if you can approach them with some different ideas, and I look forward to seeing what you come up with in class.